Okay, I would like to welcome everyone to the ABCD-GIS presentation for September 2016. I'm Jeff Blossom with the Center for Geographic Analysis. I'll be the moderator for today's talk. With us today is Bernd Resch. Bernd is a visiting fellow of the CGA with us, and he's also a professor at University of Salzburg in the Department of Geoinformatics. So we're quite happy to have him all the way from Europe here today to explain his latest research. So with that, Bernd, I'll turn it over to you.
Thanks a lot, Jeff, for this brief introduction, and thanks a lot, Wendy and Jeff and all the CGA for always welcoming me and having me back. So my idea of today's talk is to go a little bit away from we're doing things, but more like where are the frontiers we want to touch upon and where can we go in the future. And this is obviously more of a discussion point rather than a presentation. Still, I'm going to present our research, but more focusing on the methods rather than on the applications. So I termed my talk Research Frontiers in Analyzing Social Media Data. I broadened up my talk a little bit in terms of user-generated data, not only social media data though. So how would you go from traditional spatial analysis to integrated approaches? Sorry about that. So I'm going to talk about a pretty big variety of different kinds of application areas. Again, applying different kinds of self-learning systems, semi-supervised approaches, machine learning approaches, and so on, to get to these kinds of outputs from a variety of data sources as well. So wherever you feel like you're interested in, just let me know whether I should set a focus there, or whether I just can skip other ones and better focus on different areas. Brief action. I mean, this is what we all know, right? Everybody knows this kind of thingy, where within a few years, a lot of things happen in the availability of smartphones, user-generated data in the wider sense. We know all these kinds of things, all the social media networks. We know how different kinds of sensors are just now really booming, wearable sensors in particular, including wristbands, chest belts, headsets, and so on, measuring a variety of physiological parameters, or also environmental ones. And then everybody knows these kinds of maps, basically stating that we have social media data available all over the world and about the world as well. And this is something which we're leveraging every day. And GIS science contributes a lot to the analysis of these data sources. But the question is, how do we do that? And how can we improve? And this is state of the art. And these kinds of maps, be it originating from mobile phone data, from Wi-Fi data, from Flickr, from Twitter, or whatever it is, we've known these for like 10 years, right? And this is what people are still doing. But I think it's a bit, let's say, time to move to the next level. Because this is more visualizing rather than really analyzing this, right? And then there are, I mean, everybody knows the maps of Eric Fisher, right? And they're quite questionable in terms of cartographic principles, particularly drawing order. So this is something which influences the conclusions we draw and how our analysis is actually perceived. Second thing I want to mention as state of the art is that social media and user-generated data have been acknowledged widely, not only as playing around with this new data source, but really having substantial value in making decisions in a wide variety of application areas. So Google Flu, meanwhile, shut down, as we know, but there was huge evidence that what happened in Google Flu and in correlation with tweets and web searches, we saw that, for example, in the health area, there was this very good and high correlation between those user-generated data and public data by the CDC. Explain in very few words, everybody knows what that is, right? In brief, people would tweet about and Google search different kinds of terms like flu, sickness, illness, fever, and so on. And then you could temporally and spatially analyze and view this. And this is just a temporal curve for different regions for when people were looking for these terms or when people were tweeting these terms. So tweet, blue curve, Google search is red curve. And if you overlay this with the official data, the reportings of flu cases from the CDC, you can actually see that this corresponds really well. And this has been proven in a lot of cases, right? So it's not only like social media are a new data source to play around with, but it's serious stuff. And if you do it right, you can draw like valid conclusions. So that's the state of the art. Now I want to go into what we're doing in terms of approaches that are not so much common, perhaps in other disciplines, but not in GIS science, and how we can apply those and which limitations they obviously also have. So first one, a simple one, whereabouts of people. We always know that the traditional geographic problem was that we have census data, we know where people work and where people live, but we do not know where they are in real time. This is a problem for many areas of research. So our idea was to apply a semantic association between georeferenced tweets and their respective spatiotemporal whereabouts. In other words, where do people tweet about home and where do they tweet about work? And this is not done using simple keyword-based approaches where I just look for a keyword and extract these, but in an unsupervised fashion, so totally machine learning without any manual intervention. And then we correlate these with census data and see where there is a correlation between the tweets and the census data. LDA is the unsupervised learning method, which I just mentioned. Is everybody familiar with it? LDA stands for latent dirichlet allocation. I'm just going to explain very briefly. Basically, you feed the system with a number of documents, and a document would be a tweet in this case. And for each document, LDA would identify latent topics, and topics are somewhat abstract, like sports, like politics, or something like this. So the tweet would be associated with this, and then the topics themselves again would be associated with words. So concrete words about sports would be, I don't know, game, cup, match, stadium, football, whatever, right? So that's what people would tweet. And from that, different kinds of topics are generated, and then you can interpret those topics and see what people are actually talking about without any a priori knowledge. We do not feed the system with any kind of like expectation we have or keyword-based approaches what we're looking for. Now, if we apply LDA to a number of tweets, in this case 43 million tweets from the City of London for a year, we see this. The home topic over here, the work topic over here, were pretty well extracted. Again, unsupervised fashion, we only selected them afterwards, not before. This is just a temporal visualization of this. So the home topic over here, x-axis days of the week, y-axis hours of the day. And what we see is that the intensity of tweets that talk about home in the wider sense, and this would be, and this home topic would be comprised of several words again. So home, sleep, time, good day, bad, and so on are all in the same topic, not defined by us, but that's what the approach just yielded, right? The system spit it out, basically. And what you can see in the temporal signature is that it's really low in the morning. I mean, people are still sleeping, obviously. Then it's somewhat high in the later morning, and it's really high in the later evenings. You can also see this like 1 hour time lag, if you wish, during the weekends. Like these focuses here are just shifted a bit towards the later time. Okay, just descriptive, observational. Second thing, work topic, same thing. Of course, 0 pretty much in the nights, then a lot in the mornings, but only during the weekdays. During the weekends, Sunday and Saturday over here, are pretty much empty. So pretty few occurrences. Okay, that's just topics and their temporal signature. If we now analyze this spatially, namely using Moran's I and Geddes or G, Moran's I to identify where the data set is clustered, Geddes or G to identify the actual attribute clusters. The attributes here would be the probabilities of the actual words in the tweet, these here basically, right? Then we can see this. Let's just focus on the dots for now. The red dots identify significant high clusters, meaning where people talk about work and are surrounded by people who talk about work. Okay. Not surprisingly, this is in the inner city of London, district city of London. The good thing is, if we overlay this with the UK census data, meaning the workday population, which is in the background, right? It really much complies with the rose areas there. So in other words, the red clusters pretty much comply with the red areas in the background. We'll see what this means from a statistical viewpoint in a second. So what we can say is Twitter is a quite good indicator for workday population. Second thing, census residential population and tweets about home. So where do people tweet about home and where do people actually live according to UK census? Here we can see that the background, meaning the census data, are really dispersed all over the place, and so are the tweets. And there is pretty much no correlation. If we take a look at this from a statistical viewpoint, R square, the correlation coefficient is 0.08, which is basically nothing. Whereas for the work topic, it's 0.75, which is highly significant. Okay, if we go back again, here, totally scattered around space. Here, pretty much clustered. And the clusters of the tweets correspond to the clusters of the census population. So why is the home topic so much dispersed and why does it not correlate? One of the reasons is that the tweets of the home topic, so what do people tweet about home, are clustered around transportation hubs. So this again means we took a look at the tweets. People are talking a lot about I'm going home right now. Okay. Bit of a problem because we would not be able to identify this right now in this approach in our data set, because we would need to integrate some kind of direction, right, in terms of a semantic analysis. This is something which we are applying for the future, but this explains to some degree at least why Twitter is a good indicator for work, but not for home. Okay, this was the first application. Second one is to identify latent activity / mobility / traffic patterns from Twitter again. Totally different approach, namely self-organizing maps. Again, neural network-based approach in this case. So it can basically be compared, let's say, to PCA or EOF, depending on which term you use, a dimensionality reduction tool. You have a number of input vectors. In this case, just for exemplary reasons, it's 3. And all these input vectors, we use 6 in the end, are compressed to a 2-dimensional map then. And this map is not a map in the geographic sense, but it's a map in the topological sense. So the good thing here is we have a number of different input vectors, like semantic ones, where people do tweet about what, temporal ones, when do these occur, and geographic ones, where. And all these would be somewhat close or not, like at some distance, in our input space. In reality, our input space is 6-dimensional. And then we would apply a self-organizing map approaches, which finds these best matching units and transfers it over to this 2-dimensional grid. Okay. The idea, and that's the cool thing about it, is that these best matching units are, or which are close in the input space, are also topologically close in the output space in the self-organizing map. I'm going to show you why this is important in a second when we use the geo self-organizing map. Okay, again, what do? We extract a number of topics, again with LDA, as mentioned before. Again, totally unsupervised, no a priori information whatsoever. And all these topics have different temporal signatures. So for example, topic 1, the work topic, very dominant throughout the weekdays, not very dominant at the weekend. Whereas, for example, key 3 would be this sports topic, like game, cup, match, stadium, and so on. Pretty weak topic in general, so not many tweets overall, but there are very distinct peaks. And one of them is Saturday night. Of course, games happen there. We talk about soccer games, mostly in London, obviously. And then there are two more, namely on Tuesday, Wednesday nights, which are the Champions League, FA Cup, and so on games. Okay, from a temporal viewpoint, we can identify these. There are 8 more topics, which I'm gonna get back to in a second. Now, if we feed these these data into the self-organizing map, that's what comes out. And I need to say, this is a geosum, which puts a bit more focus on the geographic positions and distances as well. So this can, to some degree, be seen as a self-organizing map with a geographic focus. And what we see here are the outputs. These light gray areas indicate areas where in the input space, these 6 dimensions I mentioned before, the input vectors would be close to each other. Whereas the dark ones, they would be far apart from each other. In other words, the bright ones would be clusters, the dark ones would be dispersed. Okay. So if we delineate these now, the clusters, we can actually see that for this topic 2, which again is the transportation topic, so train, run, back, station, and so on, for transportation topic, what we see is that the bright areas, meaning these clusters, actually represent the train stations. London Bridge over here, Paddington Station, Waterloo Station, and so on. If we feed another input data set, namely topic 3, which was the sports topic, we can see how the stadiums actually come out as clusters. O2 Stadium, Stamford Bridge, Emirates, Wembley, where are the soccer clubs play. Okay, so what the cool thing is that, okay, first of all, we identified the clusters, good already. Second thing is we have such a self-organizing map for all of the 8 topics. We saw 2 of them right now. Now, if we stack all 8 of them above each other and combine them, that's what comes out. We identify clusters that are integrated, like all 8 topics are integrated. And within each cluster, we can actually see which topic contributes how much. Okay, so for example, T1, the green one, that's the work topic, as you remember. And you can basically see that it's mostly dominant here in the inner city. Makes sense, in line with our expectations. T4, the red one, is a shopping topic, so where people would go shopping. That's surprisingly pretty much dispersed in the outskirts of the city, not at all in the inner city. And then T8 is the home topic, which is basically spatially totally dispersed. You see these blue areas in every kind of pie chart all over the place, which is in line with our previous findings, right? That the home topic does not cluster spatially, but is pretty much dispersed all over the place.
Is there any element of time in these maps?
Yes.
Okay,
Yeah.
I mean, I get that the temporal piece of it is in there, but
Yes.
when you're viewing it this way, how does that play out?
It's an integrated factor in the end, right? It's compressed.
Okay.
So there are 6 input vectors, which are 2 temporal, 2 spatial, and 2 semantic ones.
Mm-hmm.
And the temporal would be the day of the week and the hour of the day.
Okay.
Is that enough for now?
Yeah.
We can also discuss it later otherwise.
Okay.
So these 6 are compressed into this 2-dimensional representation. Okay, so now let's do the same thing with traffic events. Same method applied, meaning a self-organizing map. But in this case, with tweets on the traffic topic, and these would be the words which we're seeing in there: bus, car, drive, wait, road, stop, traffic, and so on. And then we, as a different input vector, actually 3 dimensions in this case, we use the traffic information management system by the City of London. Both of them have temporal signatures as well. They somewhat comply, but not really. They have spatial signatures, obviously. Tweets are obviously more dispersed over space, whereas the Teams messages are more concentrated in certain areas. So now if we take a look at the self-organizing map, that's what comes out. And it's a bit more complicated than the last one. But this is, again, only a self-organizing map, not a geosum, right? So all input vectors would be treated the same. And what's surprising is that the temporal ones come out very strongly. So these clusters here are not spatial, but they're temporal. For example, if you take a look at cluster 4, like over here, versus cluster 1 up here, you can see that it's the same kinds of incidents, namely works, like road work. But this cluster here is only referring to weekdays, whereas this cluster here is referring to weekends, Saturdays and Sundays. And you can also see that the work on weekdays is normally happening between 8 in the morning and 11 in the morning, whereas on the weekends, it's happening in the morning as well, like 8 to 10, but then also again in the evening from 10 to 11 p.m. Okay, just 2 observations. Or also cluster 5 over here versus cluster 6 over here. Cluster 5, red represents traffic incidents, different kinds of accidents and so on. There's a clear distinction between Thursday and Fridays and Mondays and Wednesdays, which is rather surprising. And for Thursday, Friday, these incidents happen later in the morning. I mean, mostly from 10 to 12 a.m., even to 1 p.m., whereas here on Monday to Wednesday, it happens 8 a.m. to 10 a.m. Okay. So again, these are just latent clusters without interpreting them. This is just descriptive what I'm doing right now, right? Without interpreting them, these are clusters which are just arising from the data which we have not influenced in terms of applied a priori knowledge. Now, if we apply a geosum, meaning giving more influence to the geographic parameters, then we can see that the spatial structure is somewhat coming up again. So these clusters here, all of these, are not referring so much anymore to temporal parameters, but all of them are basically pretty much delineatable in geographic space. So again, what you can see is the traffic volumes, for example, traffic volume messages, let's say, the dark red, brownish here, mostly occur in the inner city. Makes sense, it's somewhat intuitive. But on the other hand, there are different intensities in different times, in different kinds of compositions of how these clusters actually arise, right? And this is again subject to interpretation, but this at least shows us a number of things that are happening in the city, which we can respond to accordingly. Okay, and now of course, like what this was is a representation of all the 7, in this case, input vectors. So tweets, geospace, and of course time, plus all the Teams messages in the categories, severities, and everything. Now we obviously want to know how tweets relate to the Teams messages, right? Like when people talk about there's a traffic jam and stuck in traffic, and when there's an actual official message. We found out that for 2 of these categories, which I mentioned before, these here, tweets correspond pretty well. So for special events, this would be an R-square of 0.73, which is really good already. For traffic incidents, all different kinds of accidents and so on, there is also a pretty good correlation. For the other ones, for traffic volumes, there is even a negative correlation, which is a bit surprising actually. So standard traffic jam without any accident happening, just like stuck in traffic, is not really representative, and it's not for road work either. This, of course, can also be true because road work oftentimes happens during the nights where people just don't tweet much about this. Okay, now a bit of a step. Social media again, but in a totally different area, namely crisis management. Crisis management at the moment suffers, or has always suffered, a number of shortcomings, including a temporal lag of information, limited resolution of, especially, for example, remote sensing information, which is oftentimes used in crisis management. There is mostly lacking information for change detection, like before and after, and so on, right? And this obviously impedes crisis management in general. So for crowdsourced data, we know they're available instantly. And secondly, it's in situ information, so it would be information which comes directly from the ground. But this is what we know as well. There's a lot of uncertainty, like semantically, also spatially, of course, and so on. It's unstructured information, so it's not like standardized format. It's non-standardized information in terms of contents and also the data format, and there are diverse data types. Okay, so let's take a look at what we did. Our use case was the earthquake in Napa Valley in 2014, August. Again, just a spatial temporal footprint, right? During the night, we see the timeline here from midnight to like 6 in the morning. Not much happens. Towards like 3 goes totally down towards basically zero, zero tweets. Here in 15-minute intervals, by the way. And all of a sudden, totally rises, and that's it. Okay, we obviously from the temporal structure can see that there is something happening. Let's go a bit further and try to find out what's happening. This is the same data set, let's say, the same idea, just printing things and visualizing things in a spatial fashion. Here, a normal Sunday, 17th of August. Here, a week later, the day of the earthquake. We obviously see different spatial patterns and intensities. This is trivial and this is obvious, but there is a reason why I'm showing this, and I'm getting back to this in a second. So again, we used LDA, latent location, meaning extracting topics. And in this case, we actually used cascading LDA, meaning a two-phase LDA. So in the first phase, we could extract a pretty good earthquake topic, but our goal was not only to detect the earthquake, but to actually see how we can delineate damages. This was the original goal. You see how this worked, not exactly really well. So in the first LDA run, we discovered an earthquake topic with 43.3%, which is incredibly high, meaning that a certain word, earthquake in this case, would contribute to a topic with a very high probability. So in other words, this word would be dominating one of the topics. And these 43.3% normally never happen. In this case, it does because of this kind of structure, right? So then if we take out this earthquake topic and apply LDA again on this subset of data, we see again 4 different topics arising. These are the probabilities. So this is what the output of LDA basically looks like, right? It's a number of words, and they are associated with probabilities that they actually make up a certain word corpus. And this is the interpretation of it. So feeding the earthquake in the night, then reporting about the earthquake the previous night in the next morning, then damage reports, that's what we were actually looking for, and then the bucket challenge thingy. Do you know what the wine bucket challenge is? Basically corresponds to the ice bucket challenge. Arose actually from this very event, right? Napa earthquake. So people pour the wine buckets over themselves to raise awareness about damages which happen to wineries. So a bit of a question of strategy, but still, it's still, this one goes. I mean, and we detected it as well. Like, for us, it doesn't matter, but it's in there. So, okay. For these 4 topics in the cascading LDA, we again have very, very significant and strong temporal signatures. First topic, feeling the earthquake in the night. You see that there is this huge peak, like at 3 in the morning, as we saw before, and then it goes down. Second thing, feeling the earthquake or reporting about the earthquake in the next morning. You see that it goes up at like 6, 7, 8, and then it goes down over the day again. Then the damage reports, and that's the good thing for us, they just start increasing, and actually they increase further the further we progress in time. And then the wine bucket challenge, yeah, they're basically in the afternoon of the following day, right? Now finally a map again. So this is what we did in terms of identifying hotspots in these data. So again, this entire data set was used to identify spatial clusters that would represent the earthquake as an event. And the cool thing is, and now refer back to the density map from before, that even though there are a lot of tweets overall, obviously, in San Francisco, it is detected here as a cold spot, meaning that the earthquake was not really present over there. And that's a good thing, right? Because if you only take a look at this kind of map, you would say, okay, there is a huge thing going on in San Francisco, but in reality, it's actually not. So yeah, obviously, Napa is up here, which was kind of the epicenter of the earthquake. And we were able to identify a number of hotspots. The cool thing is, if we overlay this with the actual earthquake footprint of USGS, then we see that these results are actually even more wide. And this was even surprising for us that it worked that well. That like this delineation here all over the place, right? The center directly in Napa, okay, that was pretty obvious probably, but also up here is a bit surprising, and it's really well put. Okay, next step, and this was our, yeah, go ahead.
I was going to mention, so presumably the squares are concentrated where there's also lots of people. Right?
Yeah, but that's population normalized, right?
Oh, you've normalized
that's the entire point in leveling out San Francisco as well, right? Because a lot of tweets happen, and also a lot of earthquake tweets happen, but in relation to what happens all over the place, it's
okay. So I was asking if you normalize it using the population.
Yeah.
Okay.
And gray is just no data. No square, no data.
No tweet in this case, right? Yeah, right. Or actually, better speaking, no hotspots, because here we only talk about hot and cold spots, right? Yeah. I mean, not significant.
And then there's not
as well.
significant.
Yeah.
But then was there a minimum amount of tweets per grid cell?
No.
Show up on the map? Or?
I don't think that we leveled this out.
Just to clarify, so you normalize earthquake tweets by total tweets, not by total population.
Yeah, but also by total population. I have another map elsewhere which shows the same results, which is
So it's
No, I'm just-
tweets per 50,000 people, or
it's tweets and population, right? Population density and the number of tweets per cell, like per raster cell.
So when you do the hot and cold, are you what's the variable here? It's the percentage of earthquake tweets per unit tweets, total tweets, or per
And
people?
per population.
When you say "and," how do you construct the equation then?
So we normalize it by two variables, right? So like tweets talking about earthquake, normalized by number of tweets in this area, and the number of the end. I don't know. I think it was a simple multiplication in the denominator, as I remember. But I need to track this back. Okay, so this was the earthquake itself. Then our original goal was to actually detect damages, right? So we went into just doing the same thing again, only for this damage subtopic, which was obviously way fewer tweets, right? And that's what the thing looked like. Again, much damage up here in the area of Napa, but also in the wider area. Rather much cold spots, or not significant in the area of San Francisco. And if we overlay this with the HASIS modeling again, last modeling for the Napa earthquake, it again corresponds really well. Here we didn't detect this, or there was a detection where the modeling, at least, and again, it's modeled, right? This is not real damage data, actually corresponds well. Okay, so much for that, yes.
If you flip the slides back a few, go back here. The word distribution, are these the only words that you use to define a tweet is associated to any topic? I mean,
So,
or do you use other criteria to classify the tweets?
no, we don't classify the
topics?
tweets. The tweets are classified totally automatically, right?
But then you
So
apply the topic to it.
The interpretation, yes.
you interpret that
Yes.
to
So
be the
like the
topic.
right side here comes out totally automatically.
Right.
And there are, I mean, these are only the top 10 words, meaning the top 10 probability
Right.
words. There are way more.
But you interpret those top 10
Yes.
words means what?
Manual
In the
interpretation,
topic.
right? We say, okay, earthquake, then wake and awake was in there as well, and so on.
Mhm.
This was why damage in there. That's why we. So that's a manual interpretation. This is we have not found a way to interpret it yet. We've also, I haven't shown this, but we've also validated this statistically using precision recall and F-score for the actual detection. But this interpretation is still a manual step. Yes. Okay. Now this is going to be a bit of a jump because this is only methodological and not at all like driven from an application viewpoint. Scaling autocorrelation. One big problem which we're having with spatial autocorrelation or the LISA measures is that they take a look at a point, take a look at a radius, take all points in this radius, and see where there's clustering or not, right? The problem with this is that this definitely mixes up events on different scales. Let me go one step further and then back again. This is an artificial data set. This is a Twitter data set from London. So, for example, we have two processes which are generated. One is a large-scale process, like larger distances, whereas this one is a small-scale process, like smaller distances between points, right? So they're totally distinct. Artificial data set, not talking about any application. Now, obviously, spatially, they're overlapping. So there is some interaction between those two processes. And if you just apply Locrimerance I, get this or G, and so on, to this kind of data set, like sub-data set in here, then you obviously mix up the two and they influence each other, right? Even though they would be actually distinct. For tweets, it's obviously not that easy because you just have this like bunch of data and you don't see like what you're looking for, and we do not know basically anything about the generating processes of tweets. Still, what we try to do is to create this scale-dependent indicator. Basically, it means that we look in the search radius, yes, but we define a range, let's say a ring, if you wish, in which we actually look for correlations. So, for example, this would be, for example, within the defined distance. This would be out of the distance because it's too small. This would be out of the distance because it's too large, right? So that's basically a subset. What we do with this is this. If we take a look at probably most of the data sets, especially social media data sets, we can see that at different scales, so this is the radius in which we're actually looking for data, right? Increasing the number of points under investigation. We can actually see the different scale ranges, again, rings, right? Contribute to the variance of the data set, obviously. So if we have a search radius of 1,000 meters, these distances, like 1 to 30 meters, 100 to 50, 500, 1,000, contribute to the variance of the data set because there are different processes which are happening on different levels, right? So now if we only want to extract one of these, this is just not possible with current LISA methods because they just mix it up. There is no distinction between distances between tweets in this case, or points in general. The problem with this is you will generate these kinds of dominant scales, right? So there will be a lot of points which have a distance at a certain scale, like here, for example. But the problem is, okay, what if I want to find out about anything else? Like this, for example, right? One of the, I don't know, let's say a Twitter data set about a city might contain the entire city as a whole, has a signature already, right? Then let's say there is a festival. The festival would have a signature, and the single concerts within the festival would again have a certain signature, right? In terms of how interactions and correlations between tweets actually happen. And this would not be possible to be detected. And in these dominant scales, you might have one scale which is totally dominant. So we developed this scale-dependent indicator. Just a little bit of mathematics, and I'm not going to go into detail. This is GIS star, basically connecting every element to every element, right? Weighting with a weighting matrix and the attribute value. And what we did is to extend this to a restriction to certain spatial scales. And in other words, an element would only be investigated if it fits our scale of investigation. If it's too close, it's not. If it's too far, it's not investigated either. Yeah, that's the mathematics. We extended this by checking the distance between I, the element under investigation, and JK, like another element, and the distance between, well, like then J and K. Okay, if we apply this to our Twitter data set, we can see the differences in the results. Here in the left column, we see the original GIS star method. Here we see our GS star, which is scale dependent, in the right column. What we've seen with the original method is that these clusters, which are identified, just get more and more and more, right? You basically add up, which is logical, because you just add more and more points, which will naturally more or less identify more clusters. Whereas with our method, you can distinctly see that different clusters are not present at higher scales than at lower ones. For example, this blue one here is not over here. Let's see, I don't know, this red one here is not over here, and this red one down here is not over here as well, because they might be and are definitely at different spatial levels. So, okay, there is a follow-up paper on topological outliers just has appeared like 2 weeks ago in PLOS ONE. I haven't integrated it here, but this might be an interesting read as well. This has appeared in IGGS. Yeah.
But your distance that is determined by your knowledge of the data set, right?
Yeah, I mean here, like you mean like how we determine the intervals?
Yeah.
Yeah.
So what would happen if you apply, you let the algorithm repeat itself using different breaks of the distance, and then let the algorithm detect what would be a reasonable range? Would that be implementable?
Yeah, that's a really good point. I think it would be, because like what this is just an example, right? We always assume that people would know what they're looking for, and then you can apply it to only look for a certain scale range. What you're saying and suggesting is an incredibly good point, because this would give you a totally different indication and conclusions about what the data set actually looks like. I agree. So the question would be, what are the dominant scales in the end, right? Like how much of the variance is made up by a certain scale range? And then the question is like, how do you make up the scale range? Whether it's like how many meters, right? Why is that 1 to 30 and not 1 to 15 and then 50 to 30? And this is something which I don't know how to tackle with tweets at all.
You would still need some knowledge about the nature of the data to set some boundaries, but then at least you would allow the algorithm to reveal what is the logical break in the scale in the middle.
Exactly, something like this, right? You would have to have a goal of having this look like a certain fashion. Like if you want to have all of these like in the same portion of the pie chart, if you want to find out like one dominant one, if you have, let's say, equal spatial intervals, distance intervals, and so on. So you always need to apply one kind of goal, and then that's. Yeah. But that would be a good learning approach. Okay, so this was the excursion. So just very briefly, I have two more application areas. One of them is defining catchment areas for mobile phone data, And the second one is urban motions, which most of you, I guess, know, so I'm just going to touch upon it quickly. Catchments for mobile phone networks. Catchment areas of medical facilities in this case, by the way. So hospital catchment areas, as everybody knows, are essential to know, right, for estimating the quality of health care system, but also to maximize the efficiency in interacting with patients and health service provision. So current approaches or previous approaches have mostly focused on really far-reaching assumptions in terms of their patients, meaning they were using census data, so where people live, distances, or travel times, or gravity models between centers of population, and so on. All these give an indication like what might happen, but it doesn't really say what happens. So what we did is to use real data, if you wish, like real patient data, using anonymized mobile and landline phone data. And obviously this is disputable, and we're going to do this probably in a second. And we tried to identify areas in which people actually use a hospital. So not in which we think that they do, but actually do. When do they call, and from where do they call from? That's a bit trickier as it sounds. Data sources, we digitized 117 hospitals, in this case in Trinidad and Tobago, by the way, just because we had the mobile phone data from there. Call data records, 2.5 billion calls over an interval of 6 months. And then, of course, all the mobile phone cells. So basically, if we take a look at where people were calling a hospital from, this is what it looks like. So Cora Chest Hospital indicates or represents a very specialized hospital. It's the only one in the country, chest hospital. So it's natural that we see, in average, larger distances. People would travel from all over the country, but it's only few people in general, because it doesn't serve a general population. Whereas on the other hand, Port of Spain is the largest agglomeration area in there. People would also come from all over the place and all over the country. But yeah, you can't really see this here. But most of them are served within this big agglomeration area in here. General hospital, so most people just go there. Again, spider map, just a very simple visualization. Now, how did we determine Serbia's the catchment areas? So first of all, we had to determine the service areas. So what we had was the points of the mobile cells. So where are the cells? We did not know, I should have mentioned this before probably, for each call, we do not know which exact location it went from, so no triangulation, but we just know about the cell which it has originated from. And the cell, a mobile cell, again represents a certain area, right? Clear. In this area, again, is divided into rings, if you wish. So the closer you are to an antenna, the more likely you are to be connected to it. Okay. So first of all, we determined the service areas for all the mobile cells up here. Then we identified calls to hospital landline numbers. That was the good thing. That was the easy part, basically. So we said, okay, we have the hospital itself. We know what the landline number is, and we see where people actually call from which cell. Then we identified calls to and from cell phones located within the hospital. This was a bit trickier because we had to overlap the hospital, which is the red rectangle here, with all the mobile cells it actually covers. And then we computed the catchment areas for each hospital by basically summing those two up. And then we could see, I don't know how much we should go in detail, perhaps not too much. We could see how many calls went from a certain grid cell, in this case, then 1 by 1 kilometer, to a certain hospital. Okay. The catchment areas look like this. We took out 4 different hospitals. We see again Cora Chest Hospital, so it's a very specialized hospital. You see that the main agglomeration area is still dominant up here, but basically people come from all over the place. Then Sangre Grande is a general hospital in a rather rural area, so it has a very strong local focus, but also few people come over from the larger agglomeration area. Port of Spain has a huge catchment area over here, which is the largest urban area. It also even goes down to San Fernando and Sangre Grande, the other bigger cities, yes.
So this is the count, not normalized, not density. Right, this represents the
Yes.
number
Yeah,
here,
yeah,
represents
exactly.
the actual
And what
total
I-
counts.
Exactly.
It
and what I
doesn't
should-
matter how many people live in which area.
And this is what I should mention is that the legend is not comparable. You observe this, right? So you see that for Sangre Grande and for Port of Spain, we have the same classes, but for the other ones, we don't. Different reasons for this, but so it's not one-to-one comparable between the maps, but it's only comparable in terms of which area they reach and cover. Okay. Okay, so the conclusion which we can draw is that there are different spatial patterns for different hospitals. And obviously, we still need to validate this because we didn't find any like comparable studies, and we did not find catchment areas for hospitals as they're defined by hospitals. So we're thinking about is getting back to the hospitals and telling or having them tell us where the patients actually are and where they come from, and then we could run through this as well. Okay, and then finally, quickly urban motions. I guess most of you remember, right? The CGA people, of course. Basically, what we try to do is to extract emotion information and then use it for urban planning, so citizen-centric urban planning. And we try to extract this emotion information from 3 different sources, namely crowdsourced data, social media, then measurements, really. So these chest belts, these wristbands, which I briefly mentioned in the introduction, measuring number of physiological parameters from which you can derive emotions or not. And then a people as sensors app, like an e-diary app, where people would tell us like what they're feeling. But this is only connected to the sensors. Okay, so this is just a short update because this was what happened like pretty much a year ago, right? And I think, I don't know whether I presented it yet, but thanks everybody again for contributing, especially Giovanni for biking around, and for everybody to help us recruit test persons as well. So we found a number of test persons and let them bike around. So they were wearing a chest belt below, which you can see right now, a camera, then a wristband as well, measuring skin conductivity, heartbeat, ECG, body temperature, and so on. So a number of parameters which we amalgamate and extract emotions from. And yeah, the analysis, I just think I'm going to skip it for now. But the outcome is this, and this needs to be discussed either with the city or whoever. Then you can at least identify a few places of like moments of emotion and stress, which are not really surprising, right? Like Central Square over here, a lot of things happen because we have the video footage of our test persons, right? So when we took a look at there, I'm going to show you in a second. It was funny things sometimes. You could see down here, which was actually there was a measure taken by urban planning. I saw, right? Because I heard that at this place, I think how many was that? Like 15 people a year died in traffic and bike accidents. Don't know where I heard this from, but now they totally restructured the intersection here with what is Marlborough Street or Beacon Street, the first one. So they have a separate bike lane, which is totally separate from all the trucks and so on, which is colored and everything. So obviously, like they realize as well. Okay, so this is based on about, I don't know, 4 or 5 million measurements of these with these physiological sensors, and we could identify a number of moments of stress and emotions there. Yeah, that's it for now. So these were all right as integrated. If we take a look at the single person, this is where I wrote down, right? Down Mass Ave, basically, and over the bridge. And the cool thing is our sensors would tell the person on the mobile phone when something happens. So when a spike is detected, an emotion is detected, the person would be asked, okay, what happened? Because just from the signal, we can unfortunately not detect it. And then they would be able to input things via our app. And these are just the app inputs here, right? And yeah, so you wrote down Mass Ave there. The indication was a pedestrian crossing. So you can see the person waiting here. He was breaking down. the car was still overtaking him, so there was something which obviously frightened him a little. Another funny thing was this one here, a bit further down. You know that, or you realize that the subway station is over there. So there were 2 pedestrians crossing, a car over there as well, so a lot going on as well. Now, what he did was, if he continues, to cross the street over there, because he had to bring back his subway bike, and you see the traffic was, yeah, rather heavy, so he had to wait a little, and it's not surprising that he actually faced some moments of stress. Oh, was that it? Yeah, okay. So he obviously crossed the street via the zebra crossing, the pedestrian walkway, basically, on the other side of the street, and went to the subway station. So the conclusion from this is that we could rather well identify like where people face these different kinds of emotions. I'm going to show you in a second which emotions these were as well, and why they did. And these were 2 of the 3 data sources, right? Namely, all the measurements taken by different kinds of sensors, and the People as Sensors app, which would be dedicated inputs, like when people think they felt something. And now the 3rd data source would be the social media data again, right? And this is something which I just briefly like to show you, because it's a semi-supervised learning approach as well, which is a bit beyond our standard approaches which we see in ArcGIS and so on. So again, we try to extract emotions from social media. Where do people talk about what, and how like do they express their emotion? So we started from raw tweets and wanted to get towards labeled tweets. Labeled tweets meaning every tweet would be assigned an emotion. It can also be none, obviously, which is the majority. So first of all, we produced a gold standard with manual labeling, right? So we had 7 annotators, which each annotated 400 tweets, saying, okay, this tweet happiness, this tweet sadness, this tweet anger, and so on, right? So we would click through, and then we basically take a look at how many labeled the same tweet, and then from these gold standard, start a growing algorithm, which would then label out clusters, let's say, of tweets with the same emotion. And for this, first of all, we did a similarity computation from the unlabeled tweets. So the similarity, and that's the most important part here, is in 3 dimensions. We basically talk about distances. And distance in geographic space, obviously, right? Let's say Walter Tobler's first law of geography. People talk about the same thing might be similar in space as well, like close to each other. Then temporally, same thing. When 2 people talk about the same thing in time, like close to each other, it might have something to do with each other. The 3rd thing was semantically. So when people talk about really semantically, content-wise about the same thing, it might have something to do with each other. And for each of those, we applied a number of features. I think it was like 9 feature groups in semantics, like word length, the words themselves. It was emojis, different kinds of the ANU expressions, effective norms for English words, and so on. From these similarities, we constructed a graph. So the nodes would be the tweets, and the edges would be the connections between 2 tweets, meaning how similar they are in these 3 dimensions: temporal, geographic, semantic. And the thicker, let's say, the edges, the higher the similarities. And then from there, we applied a graph-based machine learning approach, which basically did the growing for us, meaning delineating the clusters of the same emotions in time and space. And what came out, let's say, was this. Okay, the statistical evaluation said that at least our approach performs better than different baselines. Majority baseline means labeling all of the tweets with the class that occurs most, in this case happiness. And random baseline means just applying whatever label. That's a good thing. On the other hand, there is still a way for improvement. So these are the classified emotions for Boston. By the way, we use TGA's dataset, thankfully. for the 2 weeks around the Boston Marathon, like 1 week before, 1 week after. And we observed this, and the vast majority, okay, there is no legend. So green is happiness tweets, blue is sadness, then purple is fear, and this pink one is anger. So what you can see there, so these are the 4 basic emotions which are defined by emotion psychologists, so this was not our invention. What you can see there is that there is a huge dominance of happiness tweets, which is a known effect because the data set is totally skewed. So psychological and sociological studies have proven this, that people would more like talk out when they proudly present something and not share their sorrow with everybody and their innermost feelings. And the second thing is that surprisingly many tweets after the Boston Marathon bombing were actually labeled as happiness, which is logical, because many people were expressing their positivism, right? Like love to all of you, and we're proud of this city, we stand together and we need to go on, and so on, right? So these would be emotional tweets as well, but did not express sadness in this sense, but happiness as by the defined by the emotion psychologists. So there's a skewed data set. There are obviously, this is just the happiness tweets, there are obviously clusters as well, whereby cluster is just a density cluster, right? So it's just more tweets over here, not interpreting anything in terms of qualitative conclusions. Okay, so what are my conclusions of the last like 50 minutes of talk or so? And it's only one slide. First of all, we need to think about whether our analysis methods, which we have used for ages, whether it be, I don't know, clustering or densities and so on, are actually still valid, and whether we can actually just apply them as they are to tweets and other social media data sets, because we have always applied them and they have been designed for these structured data sets where we know what the data sets are, which characteristics they have, and so on. For social media, we don't. And this particularly applies to the first law of geography, which is not a law anywhere, right? As we know, that even though, or let's put it from another perspective, the first law of geography may and probably is not true for tweets and social media posts. It is not proven yet, and we're working on this, but on the other hand, it seems pretty obvious. So I think we need to think about different kinds of interdisciplinary methods coming from computer science, coming from computational linguistics, coming from signal analysis, and so on, especially as from pure, if you wish, mathematics. I mean, in the end, mathematics is all which we're doing anyway, right? Where we click a button in ArcGIS, we execute a formula. Furthermore, geographic position plus attributes. So calculating densities is just not so much, I don't know, the best way to do things when analyzing social media posts anymore, because we just don't know what we're actually analyzing, just spatial densities, right? So the attributes there are questionable, and we need to think about which these are. Of course, I'm up for any kind of collaboration in this sense. There is much more going on in our research group as well, ranging from augmented reality to 3-4D visualizations, to consumer and behavior patterns and so on. So if you wish, just drop me a line. I'm here also until Monday still in Boston. And of course, nothing of these happens without any collaboration. So thanks to all my contributors, be it PhD students, master students, project staff, and so on. So obviously there's always a lot going on. Well, I thank you for attending, listening so carefully, also putting questions, and I'm open for more discussions, of course. Thank you very much.
So we have a few minutes here for additional questions.
Or a coffee afterwards.
Yeah.
While people are thinking of questions, may I?
Yeah, great.
Last Friday, I attended a different seminar, maybe some of you guys are there too, which was the data science at the New York Times seminar by QSS. Were you there too?
No, I saw it.
Yeah. So the speaker made a very funny statement, which really, drilled to my mind, is the saying that we have so much data, right? So particularly social network generate so much data. And by conventional means, if you take the data and you torture it enough, it will confess anything you like to hear.
That's probably any kind of correlation, right?
I think it's well said. And that's therefore, methodology is really important and really, I think.
That's a saying, right? The good thing about correlations is you will always find a correlation. The bad thing is you will always find a correlation.
Yeah.
And
Yeah.
this is
So how much does it really tell you, or
Yeah.
what value does it add?
Exactly.
Right? Other than confirming what you already believe, and how do you differentiate those who are, really looking for just confirmation versus really discovery?
exactly.
I'd like to hear your opinion on,
That's
what's
the
the
point of
best
anti-talk, right?
practice and,
That's the point of my anti-talk. I mean, let's take self-organizing maps, for example. If you take a look at papers which talk about self-organizing maps, they have data and the analysis and blah, blah, and then they put out the self-organizing maps and then conclusion. There is no evaluation, validation, so on, because people just don't know how to do it, and there is no standardized way to do it, right? It's not like you apply Pearson's R or whatever. It's just like, that is it. And it's mostly only descriptive conclusions either. And this was one of the points I was trying to raise. We need to find ways how to evaluate our findings as well. And the problem is mostly you will have to use external data sources. But then the question is, what have you found which is not there already? And on the other hand, if I take a look, for example, at these results, this is not comparable to anything, right? Because this does not only say people are emotional in places, but our indicator has 3 input dimensions, namely space, time, and semantics, right? So if I only use semantics, the map will obviously look different, and then I can't compare the two anymore. So this is the wicked thing which we're really fighting with, that most disciplines work like that. You say, there is a method. It has been developed for 20 years, and I try to challenge the method and prove that mine is better, performs better. I mean, you see it in the evaluations as well, right? You compare against random baselines, you can compare against majority baselines, and you perhaps compare it to another approach or so, right? You can add columns there. But then the question is, how are they actually comparable if they are interdisciplinary? Because the conclusions which you draw from this is totally different than just from a semantic analysis. This is something which would acceptable as well by reviewers, because most reviewers just have their standard evaluation metrics, and you tell them that you can't apply these, but they still want to see the evaluation, and then it's like, how do you do this?
Go ahead.
Yeah.
I was going to ask about the LDA. How long did it take to compute the LDA? I heard it can be expensive, but I'm just curious from your.
Yeah, no, it is. In this case, 2 to 3 hours, but this was only, let me think about how many tweets this was, about 1 million.
Oh.
So that's still reasonable. We're thinking about doing this in real time as well, right? Like just moving window basically, and then, and I think it's feasible if you parallelize it better and you put it on better machines. I mean, we just did it in our standard machines. Which
You found it to be parallelizable? LDA is parallelizable?
Yeah.
Oh, okay. But there was something that was, I remember researching this kind of stuff once, and there was
Mhm.
LDA, and there was something else, and somewhere in there I thought it was an n cubed situation where n is the number of records, and so at least that was back in when it was developed back in the actually late 80s, which was kind of surprising.
Yeah, obviously not all steps are parallelizable, right? Like building
but I'm
focus and
not-
everything, but yeah.
You know, I didn't really use it, so, okay. Maybe our methods have improved since, I would hope so, since 1989.
I mean, people have not used it on extensive data sets so far, right? Because it was designed for structured text, meaning, let's say I have a newspaper article and then you have 100 of those. These are many words, but few documents. But if you have a lot of documents, then like this squared nature really gets to you.
So tweets are great, right? You have a lot of, decent amount of people on Twitter, but I think, there's a heck of a lot more who send text messages. Have you looked into obtaining those from a cell phone company, de-identify text messages and their locations, or has anyone tried to look at that sort of thing?
So me personally, I've never had access to mobile phone data which provides semantic information.
What about the Trinidad Tobago data? Wasn't that phone?
Yes, but no semantic information, right? It's just positions, calls, call duration,
But no content.
anonymized identifiers and so on. So no semantic information so far. This would be definitely something which is a huge data source. The mobile phone companies which I was in contact with are understandably more than reluctant to give this information out.
Right.
Because that tells a wholly different story, right?
It's also very hard to anonymize.
Yeah.
Exactly. And the thing is, I mean, we know that location is a very strong proxy for identity, right? I mean, the Montoya and everything at MIT proved more or less. I wouldn't really support this case, but still, they stated in their paper that 4 locations are enough to identify a person, like work, home, shopping, whatever, which may not be true in most cases, might be true in optimal cases. But still, I mean, you could, if you wanted, probably still derive information about people. On the other hand, it's anonymized in terms of numbers, and it's anonymized in space over the cells, right? We do not know where people actually called from, but just a certain range, which is large in rural areas, for example, right? Which is good because there are few people living.
Back to your piece on figuring out where home is and work is. Of course, a major way that's done is by looking at patterns over time for an individual user.
Mhm.
But you didn't use that aspect of the tweets at all for that. And was there a reason why?
Well, that's a question of the actual usability and the way to find it out, right? We just used tweets as points, not as trajectories. So the user ID does not play a role so far here.
No, which is fine. I'm just wondering.
Okay.
Yeah.
Then
is there
I
a reason why
misinterpreted
you
your
wouldn't
question.
take advantage of that aspect, or wasn't that the goal of the? Why wouldn't you take advantage of that aspect? Of
Sorry,
the
could you rephrase the question? Perhaps I misunderstood it.
If you're trying to figure out where home is and where work is accurately, why not use the patterns that individual users in space and time create?
Yeah.
Which are commonly being used to figure out where home is.
Totally. That's a different kind of analysis. I agree.
Right. Okay.
So
That would have been cheating to use that approach.
I don't know. I think it would just add strength to the outputs in the end. In this case, we didn't, right? And this is definitely an addition we should think about.
Yeah. Okay.
I mean, trajectory analysis and trajectory clustering is definitely not our main expertise, but still.
But
Yeah.
I'm also asking that in the context of some of your other vignettes, where you're talking about using space-time semantic clustering altogether, and you had that in a couple different places. You had it with the self-organizing maps, and you had it. So if you're using space-time and semantic things together, I'm just saying, the patterns in time and space, when you can leverage them, you want to use them. That's why I was asking. So, which leads me to a question. The self-organizing maps are really interesting. I didn't totally understand them, and so I guess one question is, so these basically are those hexagons are basically end up representing clusters in space-time semantics.
The hexagons are just the best matching units. So they basically stand by themselves.
What is the unit? What does unit mean in that context?
It's a spatial unit, but not a geospatial, right? It's not geospatial. It's in the input space, right? This input space has several dimensions, including temporal, semantic, geographic, and so on. So the output is not geographic by itself.
No, that's what. So clustering is a better way to think about it.
Yeah.
Than
Yeah.
space.
Yeah. Exactly.
So those hexagons represent clusters in
Yeah.
space-time semantic
Whatever you fit
dimension,
into. Exactly.
land, wherever that is.
Right.
Oh, so you
So-
couldn't have overlaid that, I was thinking, and maybe this is false, that could have been superimposed over a real world map, but now what?
There's no relation,
So-
right? But some
No,
of
there
them
isn't.
do have
It's
place
totally-
names on them.
Yeah.
But those place
Yeah, they
names
do.
don't line
Two different things, right?
Yeah.
This is what I was mentioning. This is a self-organizing map. This is a
completely
geosum.
ungeographic.
exact. No, it's not completely on because we
right.
feed geo in there as
Yeah,
well, the
yeah,
positions. So there is some part in there, but you could not say this is north and this is south, west.
It's only in there in that it's in there as a dimension in the cluster.
Yes. And that's
It's
why I
not in
mentioned.
there in the layout of that. entity.
Exactly.
That's-
It's always compressed to a two-dimensional, it's even called a map, right?
Right.
Self-organizing map, but it's not the map in the geospatial sense. And that's why I mentioned as well that here you see that the temporal dimensions are actually dominant because the clusters which you see
They've
are the
organized
temporal
themselves.
ones.
That's the
Exactly.
O in the
Exactly.
SON. They've
Whereas
organized themselves by
If
time,
you,
whereas the other, they've organized themselves by location.
yes. Whereas if you use, instead of the self-organizing map, a geosum, which puts more focus to the geographic components, then you can say this is somewhat geospatial. Or on the other hand, I mean, it's not about overlaying maps or so, but at least you can say, okay, these clusters have a special component in that you can, for example, see Paddington Station, the stadiums and so on, right? These are basically areas in the city, if you wish.
Mhm. Yeah.
Still not 100% pinned down, but
Yeah. And the fact that the cluster that's on the top is on the top and the cluster that's on the bottom is on the bottom is due to the way in which you're probably reading, your algorithm is reading through the data and starting to throw clusters into the hexagonal cells. And it goes through a particular process. I'm just wondering, I guess, what distance does mean there. And does it mean, I guess it means distance with regard to the space-time semantic space, whatever that is.
yes,
So if
exactly.
something's on the top, it's really far from
Exactly.
a cluster on the bottom. They're very, very different space-time semantic cluster-wise.
Exactly. So, yeah, that's the exact point.
Space.
That's the exact
Is
point.
that-
It's a mathematical space.
It's a mathematical
A
space.
totally virtual one,
And
right?
this is projected mathematical space from multiple dimension into a two.
Exactly.
Well, but it's all ordered from 1 at the upper left to the 29 at the lower right.
So,
And the order is determined by you, right, when you set up the model? CP1,
No.
CP2, CP3, CP4. That's
okay,
all.
yeah. I mean, that's what we labeled, right? This was
Okay,
manually
so that-
labeled.
that-
Yeah.
That's a
So
label.
we have delineated
Sure.
it just to point out the cluster.
To organize.
The map would look something like this, right? Just like black and white shades.
That's just
That's
after the fact.
And then you can see, okay, I have, I don't know, a huge cluster here. Let's take a look. And when we took a look at the tweets, like which tweets there are, we find out that they're all, I don't know, in this case, surrounding a station basically, right? Because that's the train time.
Did you have to do some validation of what of the factors of the data was making them into a cluster?
Yeah,
Or was
that's
it,
determined by the component planes here.
okay.
These are the 6 input dimensions. I didn't mention them in the
Okay, and so these
presentation
are
at
for
all.
CP1, and then you can.
So component planes means these are the single dimensions
Yeah.
for each of which such a self-organizing map is produced. So obviously, if you take a look at the geographic ones, they have a geographic component inherently. But then LDA, time and time is just totally a geospatial, right? Then if you overlay those, you just mingle all different kinds of space.
I think-
Whereas this one again, of course, like you see the geo up here, right? Just to confuse you more.
The labeling of these clusters is very similar in concept to unsupervised classification of multispectrum images
Mhm.
in my mind, right? You take the spectrum readings of the stack of images And without knowing which is which, you just classify them, which is like cluster. And then afterwards, you take each identified cluster or class and then assign land use or whatever you
Yeah,
were
exactly.
trying to get out based on what you understand in the content. of
Yes.
it.
So the labels in there are just our manual interpretation. And the drawings, like the colors, are also manual, right? They did not emerge.
Do you decide how many you get, or does it just give you a distinguishable number?
You decide how many columns and rows you want. This is mostly determined by the nature of the data.
But the number of clusters you get is really what you decide are clusters.
No. I mean,
Well, yeah.
yeah,
I mean,
okay.
you're
You
saying-
decide, yeah, that's right. I mean, but on the other hand, we just delineate the really bright ones, right?
You're saying the bright ones are clusters.
Yeah,
we delineate those.
Right.
But if you want
Exactly.
another level
I mean-
of clustering,
Mhm.
or if you wanted to say the two brightest were a cluster,
Yes.
then you'd have different.
Yeah.
Which brings me to a question. So if you had, each of those indicate, each of the 6 dimensions, are they all, they each have built-in like a sensitivity level inherent in the way you are using them to define clusters?
What do you mean the sensitivity in this case?
Well, for space, you've got some kind of distance, some kind of thresholds that you're using to determine whether things are close or not,
Mhm.
whether they end up having an impact
Oh, yeah. Right.
cluster-wise. For semantics, you have some semantic distance thresholds built into your
Yeah.
algorithm, right?
Yeah.
So then you could imagine in an application in which you had a knob for each of those 6, right? And if
Totally.
you just had this image right now, but turned the space knob a little bit, these might be organized into quite different clusters.
Totally. This is
And
a.
that could be done with any of these. And it would be interesting to do that because then a human being could actually start to see what was going on and see how things matched their vision of reality, whatever that might be. Which is kind of what you're doing here, but you're doing it as a snapshot.
I totally agree. So there are actually 2 aspects to this. One is the self-organizing map, the inputs and thresholds, if you wish, the sensitivity. And this also applies to the input data already, which is the LDA output, right? And for LDA, you also have a few screws which you can adjust. So that the topics actually came out like this is not natural, right? Different parameters could yield different topics and different signatures. So that's definitely something. Again, it's what we're looking for and then try to adapt it. And there are, for some parameters, there are formalized ways to find them, like the number of topics and so on, which is defined by the number of words, number of documents and so on. For others, there are basically not. And especially for the last one, which I showed, the urban motion thingy, we fiddled around a lot, especially with how do you define spatial and temporal decay for tweets. There is no informed way to actually do this. There are a few papers on this, but
So it's
mostly
strikes me
guesses.
that one practical application could be something like, where you're trying to figure out the relationship between tweets and as an indicator for actual census, or, population density, or other kinds of demographics that we know about through census, right? So if you tuned that for a particular place where you had good census data, such an approach might be usable in a place where there is less good census data or there's no census data. Or say for voting districts, you can do the same thing.
Yeah.
I mean, it seems like a huge application space for this would be in using social media data, data to come up with better usable data, say government, the kinds of data that governments typically produce, but for places, there are lots of parts of the world where they don't have good government data. They can't make good decisions about how to allocate resources, for a hospital or whatever. But the social media flow in that area could be harnessed.
And that's obviously applicable to a number of application areas, right? If you think about disaster management, I mean, disaster management managers are still struggling with actually getting results out there. So we say, okay, obviously social media can support you in making decisions, and if you feed them into your models, they might improve in quality. That's the entire conclusion here.
So let me cut in. We're out
Yeah.
of time. We need to vacate the
Oh,
room. But
yeah.
thanks again for speaking.
Thank you very much.